In this video, I want to look at another example of using annihilators to find the particular solution for a non-homogeneous nth order differential equation. Um, and to point out that this method works for all n that are positive integers, including, say, 1. So I want to do a first order non-homogeneous equation and show how we can use this method that we're doing for higher order stuff back on first order things. So the differential equation I want to look at here is y prime plus 3y equals the sine of 2t. Okay. Now, this is a first order linear differential equation, and we have a method for solving that. In fact, I'm going to use that method later in the video to see how it compares to this method of annihilators. So I take a look at that left-hand side, and I say, well, I can write that as d plus 3 of y equals sine of 2t. Now, if this was a homogeneous equation, that is, if this was a 0 right here, then I could see that the solution to that homogeneous equation would be c, or the general solution would be c e to the negative 3t. And I get that because with that homogeneous equation, I would say, oh, I'm expecting y equals e to the rt, plug it in, you'd get a characteristic equation of r plus 3 equals 0, so r would equal minus 3, and e to the minus 3 would be the solution. Right? That's not how we did it back in chapter 2, but we could have. Right. So anyway, I can see what the homogeneous solution would look like. Now I need to find one particular solution. And to find the particular solution, I'm going to apply a differential operator. Now, what is the annihilator of sine of 2t? Now, this is a little trickier to find than the ones we did in the previous video. However, thinking about the result we got, or where those annihilators came from, or where the functions came from, or anyway, the tie between them all, is that if I know what factors of the characteristic polynomial create the solutions, then I know that same differential operator is going to be the annihilator. So in order to get a sine of 2t, that would come from a fact, well, with r equal to 2i, right? There's no exponential decay part, there's just the sine. So r equals plus or minus 2i would create a sine and a cosine of 2t. So r is plus or minus 2i means that r plus 2i and r minus 2i are factors, and if you multiply those together, that would be r squared plus 4, right? So d squared plus 4 is my annihilator. And notice I can double check that. If I take the second derivative of the sine of 2t, well, the first derivative would be 2 cos 2t, right? There's a chain rule that pulls the 2 out. And then take the derivative again, I'd get negative 4 sine 2t. So negative 4 sine 2t plus 4 sine 2t is 0, right? So the annihilator of sine of 2t is d squared plus 4. So if I apply d squared plus 4 to both sides of this, then the right-hand side is annihilated, and there I actually do the calculations written out, and you can see that, sure enough, the d squared plus 4 does annihilate the sine of 2t. And now I'm looking at a homogeneous equation, and the solution would look like the d plus 3 would give me the e to the minus 3t, and the d squared plus 4 would give me a cos 2t and a sine 2t. Cos 2t and a sine 2t. So the particular solution that I would need for this original differential equation looks like this stuff, because the homogeneous was there originally, I still see it here, and now there's this new stuff added in, and so that's what the particular solution needs to look like. So my guess for the particular solution would be a cos 2t plus b sine 2t. And actually I'm going to solve for a and b here, because I take the derivative, and then I plug it into the differential equation, right? I plug it in to the left-hand side here. So here's the derivative plus 3 times the function, and that's supposed to be the sine of 2t. And if I collect like terms, so what's in front of the sine? There's a minus 2a, and there's a plus 3b in front of the sine, and so that has to equal 1. What's in front of cosines? There's a 2b, and and there's a 3a in front of cosine, and that has to equal 0 because there's no cosines over here. So I've got two equations with two variables, solve for a and b, and I'll leave that algebra to you, but it ends up a is minus 2/13 and b is 3/13. Easy enough to double check by just plugging it in here. For instance, the second one, you multiply a by 3, that would be -6/13, and you multiply b by 2, that would be 6/13, and sure enough they add up to 0, and you can double check that they work in the first one as well. So the general solution to this differential equation, this first order differential equation, is the homogeneous part plus the particular solution to the non-homogeneous part. Now, let's compare this to what it would look like back in chapter 2, like day 2 of this course, right? This is one of the I think this is the second type of equation that we solved, was first order linear. And so here we go. Here's what this looks like before. We would look at this thing and say, oh, there's a 1 in front of the y prime, so the integrating factor is e to the integral of p of t dt. Well, in this case, the p is just 3, and so you get e to the 3t would be my integrating factor. So you multiply both sides by e to the t. The left-hand side is exactly the derivative of this product, so that when you integrate both sides, you get this product of y times the integrating factor. But on the left-hand side, you get the integral of the integrating factor times whatever was over here to begin with, right? Now, this integral is doable by hand. You'd have to do it by parts twice, and then realize that you got back to where you started from and subtract that over to the other side of the equation and then divide by whatever coefficient's there. It's a bit of work to do the integral of an exponential times a sine or cosine. But I'm not going to do it. What I did was I just went to Wolfram Alpha and said, hey, tell me, what's the integral of this thing? And it said, oh, it's 1 over 13 times e to the t, blah, plus a constant. Okay, fine. Now divide by the integrating factor. And the e to the 3t's cancel out here. And then, but the c gets divided by the e to the 3t, so it's c e to the minus 3t. And I noticed that this is exactly the same as that. And so I wonder, why didn't I do that before? Because I do think that it was easier to do it with annihilators than it was to actually do that integral, even though I didn't do the integral. I looked it up. But if I was doing it by hand, this would be a pain in the neck. But this was not. And really the reason why we didn't do this other method before is that this other method applies when I have constant coefficients. I need a linear equation, but not just any linear equation. I need a linear equation with constant coefficients. This thing that we did back on day 2 of the course, p of t could have been any function of t. It didn't have to be a constant, right? Here it's 3, it's a constant. And so this method of annihilators, or the method of that we've been doing here, it works, but it wouldn't work if this was any function of t right here other than a constant. So this method of annihilators works nicely here because it is a constant. So anyway, again, this is not really part of the course or something I'll test you on, but I think seeing it and looking at this broadens your understanding of where some of the other stuff is coming from.